are delighted to have Olivier Darrigol today for the penultimate session of the MEPHISTO Seminar. A few words of presentation. Olivier Darrigol is an historian and philosopher of science, working at Université Paris-Diderot and also at Berkeley. Olivier has written numerous books on modern physics. He's worked on electrodynamics, statistical physics, quantum field theory. Maybe one of his most famous books, I guess, is Physics and Necessity, rationalist pursuits from the Cartesian past to the quantum present. And today you will be speaking about the principle of relativity, a line that can be traced through centuries. You have 1 hour, the floor is yours.
Well, thank you very much for this invitation. I'm very honored to be here, and I'm sorry for speaking English, but I was advised to do so. And, the title of my talk, in fact, is borrowed from Einstein. After the war, the Second World War, you remember there was a spectacular confirmation of one of the predictions of Einstein's general relativity theory, and it was a British confirmation. And Einstein gave a talk, he was invited to give a talk in London at that time. And at the beginning of the talk, he stated that relativity theory belonged to a line that can be traced through centuries. So that could be interpreted as false modesty. Today, in fact, I will try to show you that there is some truth to it, although it's not so obvious at first glance. Because, there is a received idea about in the history of relativity theory, in particular special relativity, that Poincaré and Einstein, in these theories, they extended a known principle of mechanics, of relativity, to electrodynamics. But in reality, if you look at the history of mechanics from Newton to the late 19th century, you find that for most people, and most textbook writers or whatever, there's no principle of relativity there. It doesn't occur, and it's not there. And so, are there enough exceptions to this general picture to justify Einstein's claim? And this is the question I'm trying to answer today. And indeed, there are a few characters in this story who indeed had something akin to our relativity principle. And here I have a few gallery of pictures of those people. And the first one is Christian Huygens. Second one is Immanuel Kant. Here you have the Marquis de Laplace and 3 less known figures. There is James Thomson, the engineer brother of William Thomson, alias Lord Kelvin. And you have a French engineer, physicist, pedagogue, Jean-Baptiste Bélanger, and someone even less known, Heinrich Streins, who was a physics professor, mathematical physics more, and a colleague of Boltzmann in Graz on that side. But when people write about the prehistory of relativity theory, they usually start with Galileo, thinking that there is a principle of relativity in Galileo already in the Dialogue, the famous Dialogue of Galileo of 1642. But in fact, I will argue that according to my definition of a principle, there is no principle of relativity in Galileo. And so what you really have, I think, is a law, an empirical law of what we now call restrictive relativity. Okay. So famously, Galileo was arguing against an old Aristotelian objection to the motion of the Earth, that if you drop a body, a ball, if the Earth rotates during the fall, well, it's not going to fall on the vertical line, the body, and something will fall somewhere behind. And so, in order to avoid this paradox, the solution of Galileo was to take into account the fact that from an observer at rest, who sees the Earth rotating, well, the body initially, the falling body also has an initial horizontal velocity. It moves together with the Earth, and then its velocity, according to one version of the principle of inertia, Galileo's version, it will persist, this horizontal velocity. So what you have in the end, it's a composition of this horizontal motion with a motion towards the center of the Earth. So and those two motions, in fact, give you a vertical fall. So that's Galileo. So you see that by this reasoning, you arrive at the consequence at the fact that the motion of the Earth, which is in a first approximation, simply an horizontal motion, that's the surface of the Earth, a uniform motion, it doesn't have any effect on the phenomenon of fall. And so this is, say, a third case of relativity, and which Salviati in the Dialogo immediately generalizes, and through an experiment which is half real, half thought experiment, if you will, and well, it's expressed in a very flowery manner. And lock yourself and a friend in the master cabin of a large boat and take flies, butterflies, and other small flying animals with you. Take a large tub of water with a fish in it, hang the bottles that empties drop by drop into a large container below it, etc., etc. That's what you have in this picture. And then Galileo, Salviati goes on to say, well, but if you observe all of this, you will see that the motion of the boat, if there is any, and if this motion is constant enough, you shouldn't stop the breath. Quite very clear about that. That's this uniformity of the motion required. But everything will happen as if the boat were not moving. So this is what I call a law of relativity, because it's something that you can test empirically, empirically valid. But I say that there is no principle for Galileo, because if you look carefully, I don't think there is a single instance where Galileo clearly uses this result as a principle. I mean, as a constructive principle that is used, at the beginning of a theory in order to derive other theoretical laws. He doesn't do that. So for me, principle has this, by definition, has this constructive ability, and this. That's why I think it's not a principle by my definition. And of course, this is the principle of relativity as we conceive now. It has this constructive ability. The first part, best of knowledge, the first person who really uses relativity as a constructive principle is Christian Huygens. And he does it in manuscripts first that are not dated, but we believe they were written in the 1660s, and things like that. And the manuscripts deal with the problem of elastic collisions. And so you have this picture here, extract from a later published writing of Huygens. And you see those two gentlemen here, they are performing an experience of collision of two identical balls. And one of them is on the shore, the other one is on the boat. And Huygens tells you, well, if you choose the velocity of the boat, you take a special value, which is the average of the initial velocity of the first ball and the initial and final velocity of the first balls. But this equation, it implies that during the collision, the relative velocity with respect to the boat of the first body simply changes sign. Well, the intuition on elastic collision tells you, well, if you just have some kind of reflection of the first ball, by symmetry, you should have the same thing for the other ball, it will be reflected. So you will have also this relation here. And then if you combine those two relations, you get an important law of elastic collisions, basic law of elastic collisions, that during an elastic collision of the two identical balls, here, the relative velocity simply changes sign. So this is the basic result obtained from the principle of relativity. Of course, he doesn't call it that way. He uses anachronistic wording all around. And and then interestingly, he will also use it to derive the law of Galileo's law of constant acceleration of a falling body. And which this is, in fact, this will be published at the beginning of the Horologium Osciratorium, le traité de l'horloge, on dit en français, of Huygens, and it is on clocks. And where he first deals with free fall. But the reasoning, the fact is that if you want to use a boat in the reasoning, you have to transform the vertical motion of fall into a horizontal motion. It is this with this device. See here you have your falling body, but it pulls through a thread here, and there's a pulley here, and it pulls another body that can move horizontally without friction on the table, the body A here on this picture. And now the question is, if you look at the increment of velocity of the body A after a small amount of time has elapsed, does this increment of velocity depend on the initial velocity of the body A? If it doesn't, that means that there is uniform acceleration. So that's what you want to prove. Well, in order to prove that, Galileo tells you, well, okay, suppose there is an initial velocity of the body A. I can look at the same phenomenon from the boat moving at this velocity, and then for someone in the boat, there is no initial velocity, and since the increment of velocity should be the same for an observer in the boat and for an observer on Earth, that means that the increment of velocity is independent of the initial velocity, and therefore the motion is uniformly accelerated. So you see you have two beautiful applications of the relativity principle here, genuinely to derive new laws of mechanics.
Can I ask
not so new, because you were already known.
just a small...
yes, sure, please interrupt me anytime you want.
Does Huygens explicitly refer to rectilinear relativity? Because Galileo, it's rectilinear motion, and in the case of Galileo, of course, it's circular, but you actually is usually only in the approximation, tangential approximation, where you can go locally, it's quasi-rectilinear. Okay, but it's true that Galileo has a circular inertia, as you know, so it's not the same inertia as Huygens. So Huygens is much closer. And in fact, Huygens is with Newton, there are the two first who really have exactly our principle of inertia. Because it's sometimes falsely said you have it in Descartes, but it means something different than inertia for Descartes, really. It's a misreading of it. So you really, but here you can tell that the inertia for Huygens is really the same. So anyway, I'm talking about something different here. But yes, the case of Huygens is quite clearly a case, I think, of what I want to show, that you really have a way of thinking which is akin to the relativistic way of thinking in much later years. Now what about Newton? And looking directly at the Principia Mathematica, 1687 for the first edition, there, at the beginning of the Principia, there are two corollaries to the famous three laws of motion of Newton, number 5 and 6, and in which we can identify as a modern reader what I can call a restrictive relativity theorem. It's a theorem because this is a result that is derived from the three laws of motion, two of them. So it's derived mathematically from the laws of motion. And well, I start with this first result, and it's stated in the English version.
translated from the Latin. It's stated as the motions of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forwards in a right line without any circular motion. And so here I think you clearly see, of course, in a language which is not ours, but you guess enough that means that what we identify today as a restricted relativity principle, and space is what we would call a reference system in this language, the reference frame. And it's all restricted to uniform rectilinear motion. Okay, so that's but now, more strangely from a modern reader, there is another theorem, which I call accelerative relativity theorem, which is stated as follows. If bodies anyhow move among themselves are urged in the direction of parallel lines by equal accelerated forces, they will all continue to move among themselves after the same manner as if they had been urged by no such forces. Well, to understand this, you first must know something about Newton's terminology. What Newton calls accelerated force is just, from our point of view, an acceleration impressed by some cause, external cause, and which in Newton's mind you can imagine is gravitation. So what this corollary tells you, or the theorem tells you, is that if you have a system of bodies that are globally immersed, to put it in modern terms, in a uniform gravitational field, and so they are all subjected to the same acceleration, and this common acceleration doesn't change anything to the relative motion of the bodies in the system. You say, why the hell does Newton introduce this strange principle, you will think? Well, it's a very important theorem, and not principle, for him, because it is thanks to this theorem that in the first book of the Principia, he will be able to derive the 1 over r square law, the Newton's law of gravitation, from the known observations of the motion of the satellites of Jupiter. And because suppose that Jupiter and satellites were alone in the world, nothing else acting on them, knowing Newton's law of motion, and knowing what's the observed motion of the satellites, you can infer the law of interactions between the satellites, the law of attraction between the satellites and the central body, which is Jupiter. But you can do that only if what you observe is not affected by the effect of other bodies, in particular the sun. But the fact is that by this theorem, you can ignore this the common pool of the sun on these satellite systems and around Jupiter. And that's why you can reason this way. So that's why this corollary is important for Newton. But you see, again, my main point here is that it's only theorems. You do not have a relativity principle for Newton, just as much as we didn't have one for Galileo either. Now, if you look, I jumped over a century, but in fact, if you read Euler and D'Alembert carefully in particular, you will find instances where you have something akin to a use of relativity as a principle. And it's not completely clear, and it's not so is so strongly asserted, certainly, as it is in Laplace's, Laplace Système du Monde, the first edition, the first book, first edition of the first book is in 1796. And, well, of course, to do a Système du Monde, you need a lot of mechanics, Newton's law of mechanics. And so at the beginning of this treatise, there is an exposition of the laws of Newton's law of mechanics, but something about Newton's laws as found in Newton bothered Laplace that to him it was too much to assume the second law without any justification like that. It didn't seem obvious and natural that the second law should be true from the point of view of Laplace. But first, I must remind you, I'm not sure you all know what Newton's second law was. So, because Newton's second law, you say, oh, F equals ma, etc. No, that's not Newton's second law. Newton's second law is different. It's a statement that under an impulsive force, so a force acting in a very short amount of time, an impulse, okay? There is a definite velocity increment that doesn't depend on anything but the impulse. That particular, and most important, it doesn't depend on the initial velocity of the body, this increment of velocity. That is a true Newton's second law, because Newton was thinking of forces as a rapid succession of discrete impulses. That's how he was reasoning typically. And Laplace still uses this continuous approach. And then he tells you, well, if you admit what I call the principle of relativity, restrictive relativity, this implies Newton's second law, and the reasoning is exactly as what you have seen in the case of Huygens for deriving in the case of uniform gravitation, the constant acceleration. It's the same kind of reasoning, is that the increment of velocity caused by an impulse cannot depend on the initial velocity, because you can just eliminate the initial velocity by looking at the same phenomenon from a moving reference frame, so at the initial velocity. And so that's why, and Laplace, of course, he has an entire paragraph to tell you, okay, there are a lot of observations that we have done on Earth that proves that this principle is true. And empirical truth, so it's an empirically verified, very precisely verified empirical law that you can elevate to principle and use it as a derivation of another important law of mechanics, which is Newton's second law. So you see now there is a very clear opposition between Laplace and Newton here. For Laplace, restrictive relativity is an empirical fact that can be then used as a principle to derive the second law of Newton. For Newton, restrictive relativity is exactly the reverse. It's a consequence. It's a mathematical consequence of the second law. You see, Laplace authorities in France, of course, was you all know that was very considerable, at least in the first part of the 19th century. And as a result, there were some French textbooks writers already used this reasoning by Laplace to derive in the textbooks on physics and mechanics to derive the Newton's second law. They use this relativity principle type of thinking. And but you cannot reason in this way if you adopt a more modern view of the second law as the proportionality between force and acceleration in a continuous sense, okay, for continuous motion. And continuous forces. So, and this is why Jean-Baptiste Bélanger, the engineer I was mentioning, did also a lot of important theoretical work on various kinds of mechanics. And in a major treatise on mechanics, which was translated in several languages, there was a really important book, in fact, of 1847. He introduces what he calls, and this is the first occurrence of a name of this kind, he calls it le principe des mouvements relatifs. So now, if you see principle in law, you expect to have here a principle of restrictive relativity, but no, it's another principle. I read it for you. It's a little hard to follow. when a system of material points possesses a varied rectilinear translational motion, if another point having at a certain instance the global speed of the system receives from that instant, in addition to the force necessary to make it participate in the acceleration of the system, the action of one or more forces, it takes in relation to the system the same motion that these latter forces would impart to it if the velocities and forces that relate to the common motion didn't exist. You may be lost. Who wouldn't be? But in fact, it's actually an accurate statement of what I call the accelerative principle of relativity. The same thing. This is Newton's second corollary, erected as elevated to a principle. And so it's just the idea that if you impress a common acceleration on everybody in a system of bodies, the relative motion of the system of bodies will not be affected. Now, it's not difficult from this principle to derive Newton's law of acceleration. And the way Bélanger does it is through a thought experiment. It takes two identical particles subjected to the parallel forces on the line between the two particles, F and 2F. And then, by this principle, it's easy to see that the relative motion should be the same for these two pair of forces. On the one hand, 2F, F, and on the other hand, F and 0. And from this second fact, you can very quickly derive the fact that a double force must produce double acceleration. And then, by a dichotomy and continuity, you have the general law of proportionality between force and acceleration. Well, this derivation of Newton's second law ended up to be fairly popular in France and even mandatory, I would say, in some way, because Bélanger happened to be an important member of the committee that was responsible for the reform of the baccalaureate. We all know, I suppose, what the baccalaureate is in France. And the program, there was a teaching of Newton's laws of mechanics. It was part of the program of the baccalaureate, and then it was explicitly recommended in this program to use this Bélanger, well, Bélanger was not named, but to use this derivation from the principle of relative, principe des mouvements relatifs, to use the derivation of second law, to introduce the second law in this manner to the French students for the baccalaureate. So, of course, there were a few treatises that exemplified and reproduced this kind of demonstration. Perhaps the most important, already pretty late in the century, is the Traité de physique de Jules Viol of 1883, and where you have this variance of this derivation, pretty similar. Well, this didn't quite go all the way to the end of the century, because even in France, like late in the century, the dominant view about law F equal M R dot dot, or whatever you call it, this was most commonly regarded as a definition of force. The Flourished point of view had been the point of view of Saint-Venant, Kirchhoff, and Mach, for instance, in the 19th century. And it's for Poincaré, it's actually a convention, as in Poincaré's statements on the foundations of mechanics late in the century. So, this, of course, if you don't prove a definition, so you don't need this reasoning, you don't need the principle, you need nothing, it's just a definition. So, well, I'm not going to discuss whether this rather radical change of status from an epistemological point of view of Newton's second law, which is degenerates into a mere definition, if this is something justified, or he says instead, is it possible to give to maintain a solid justification for the Bélanger approach and for Schrapping, the approach of any physicist before, is to regard this as a Newtonian law, and for Newton himself, it is a law, of course. It's not a definition, the Newton's law. I'm not going to discuss this. It's not the point of my talk. I can tell you that I am on the side of Bélanger in this story. But if you want to know, but this is not relevant so much for the rest of my story. I rather move to Poincaré, since I already mentioned his name. Well, in fact, he gave a talk, Poincaré, in 1900 for philosophers. Actually, it was on the foundations of mechanics. And this is where he defends, this rather radically conventionalist approach. So I think this is Poincaré's conventionalism at its most extreme, I think, in the case of discussion of mechanics. So he explicitly mentions the fact that the Bélanger proof was part of the baccalaureate examination. He must have had it himself and have been a victim of it during his studies, I suppose. And he tells you that this should be rejected, indeed, because you don't demonstrate a convention, you don't prove a convention, until, but of course, but he nevertheless, he mentioned names, that principle, well, it's a little variant. Bélanger was speaking of the principe des mouvements relatifs. For Poincaré, it becomes le principe du mouvement relatif, singular. And so he mentions these principles that it had been used, but what is interesting is that in another talk that Poincaré did in 1900, he will use the same phrase, principe du mouvement relatif, in the context of relativity principle applied to optics and electromagnetism. And as you probably all know that late in the century, Poincaré was first to assert the general relativity, the general validity, of the relativity principle, first relativity, to optical and electromagnetic phenomena, which other people believed would suffer exceptions. It was only true in some approximation, but Poincaré was convinced that this would be true forever, that this should actually be taken as a constructive principle for constructing those theories of electrodynamics of moving bodies, etc. And so what is interesting there is that you see that the principe du mouvement relatif was used, this expression was used in a context in which the principle was already used in a constructive manner to derive a law by Bélanger. And so this constructive connotation of the word principle is obviously kept by Poincaré. For Poincaré, actually, is very much insistent at this time of late in the century, and he has this distinction between physique des principes and the physics at the Laplacian kind of more physics, the Laplacian forces. And the physique des principes precisely is physics in which you start from general principles, and that will enable you to construct the theory, perhaps with a few other ingredients, but they are really, these principles are very basic, and they are some sort of empirical laws that have been elevated to principles. You don't question them anymore, and you use them to construct the theory. Okay, and then what happens is that in a later evolution of his thinking on relativity, Poincaré, he will use in La science et l'hypothèse, in 1902, he uses the phrase le principe de relativité, au lieu de principe du mouvement relatif. And in 1904, again, you have principle relativity, or the English version to principle relativity, because it is in the same lecture that was given in St. Louis, Missouri. Now, let's see what happened in the case of Einstein, because of course you all know that Einstein also used this expression, principe, Relativitätsprinzip, or principe Relativität in German. And well, interestingly, we have direct evidence. You mentioned the treatise by Jules Viol, where you have the Bélanger proof from the principe des mouvements relatifs of Newton's second law. This is the very treatise that Einstein used to prepare for the ETH entrance examination in 1885. By the way, he failed.
But what matters to me, well, he wouldn't fail the second time, but he failed the first time. And what matters to me is that we still have the copy that Einstein used of Euler. There are annotations in Einstein's hand in the margin of the very section in which the principe du moment relatif appears. Well, those annotations are actually not very interesting a little bit, but they prove one thing, is that Einstein had surely read this part of Jules Verne. Okay. Then we know for sure that Einstein read Poincaré and Einstein's hypothesis in 1904, and most likely in the German translation, which just appeared that year, I think. And we know that in 1905, in the famous article on the electrodynamics of moving bodies, he uses the expression principe de relativity. Last remark is that it may not have escaped your attention that what I call the accelerative principle of relativity, which is also Bélanger's principe des mouvements relatifs, that this principle, it kind of smells like Einstein's equivalence principle. This is all telling you that when you are a system of body immersed in a uniform gravitation, you can eliminate the gravity from this just at looking at it from an accelerating frame. That's just a free-falling elevator, and so this looks exactly, well, not exactly if you look in the detail, but it is similar to the equivalence principle. One major difference, of course, is that the way Einstein used this principle in 1907 was to infer consequences about non-mechanical phenomena, not essentially mechanical phenomena, of electromagnetic phenomena in particular. And whereas in the case of Bélanger, it's used in a purely mechanical context. So it acquires a new heuristic power that it didn't have in a version of Newton's accelerative principle. But of course, I don't want to speculate too much because I have certainly know. Einstein never said, "Okay, I read Viol and boom, that gave me the equivalence principle." It's not. But at least subconsciously, it is true that Einstein was aware of, had been exposed to this. To such a principle rather early in his studies, and that could have remained in his mind and eased his approach to the equivalence principle later, through the equivalence principle. Okay, so far, I have at least tried to explain you where the expression principle of relativity or principle of relativity, how it actually originated from a tradition in mechanics that goes back to Huygens and through Laplace, and then those French textbooks writer, and for pedagogical purposes, people needed a justification of Newton's second law, and they have this principle of some principle of relativity that appears there. And so there is a name, but also the idea of the constructive approach associated with a name principle, with the fact we call it a principle, this all can be explained through this prehistory of mechanics. But one other important feature of the principle of relativity is its unavoidable relation, tension, connection with another principle of mechanics, or another law of mechanics, which is the principle of inertia, which is Newton's, for Newton, as you know, is the first law of Newton mechanics. And so I think it's important to look what happens to the relativity principle when you consider explicitly its relation to inertia. Well, this is a question that was addressed by Newton in the Principia, and actually in earlier manuscripts. Actually, that was a major problem he experienced, and there are different positions he adopted in earlier versions of the Principia on this topic.
But the final idea of Newton is that, first, the principle of inertia, that's obvious. It cannot be true, to put it in modern words, it cannot be true in any reference system. It can be true only in a privileged class of system, which now we call inertial systems, right? Precisely because that's where the principle of inertia holds true. And so inertia, if you think about it, if you were not since your childhood trained to accept the principle of inertia, it's a very strange thing, the principle of inertia. Because what does it tell you? Forget everything you knew about mechanics before, but it tells you that if you take a system of bodies, say point masses, okay, that are not subject to any force at all, that are completely free, okay? Well, there is some kind of very strange pre-established harmony, we use a Laplacian word, between these bodies, because you will find that the distances between these bodies, they evolve in time, but the distances are all proportional to each other. They all remain in the same amount. So this is very strange. There is some kind of that it's like the different bodies can talk to each other to adjust their motions to each other. It's very strange. And so you need an explanation for that, at least of what Newton thought. And the explanation is, the answer to that is absolute space. You need some causal entity, some entities that has causal power in order to justify inertial behavior. And the simplest you can imagine is that there is one space, which is really, to put it in not in Newton's term, but in modern term, we say it's a kind of physical entity, this space, which causes inertial behavior. The problem that Newton had with this solution himself is that, well, if there is really an absolute space, the laws of mechanics should be different in any other space than the absolute space. But no, precisely the laws of mechanics, as Newton knows very well, they are valid in any other space moving uniformly with respect to the absolute space. And so Newton was bothered, in fact, by this conflict between the relativity principle and the assumption of an absolute space. And the way he tried to solve it, in the end, he said, well, okay, I know how to, among all this class of all possible reference frames, what we call now inertial frames, there is one privileged one, is the one in which the center of the universe is at rest. This is what I call absolute space. This didn't satisfy this principle in the list that come here, Huygens, Leibniz, and Kant. This solution, they all rejected Newton's absolute space. For Huygens, absolute space is necessarily nonsense, because there can be motion only of bodies with respect to bodies. And so when you talk to motion mechanism, must be motion with respect to a reference frame, what I call reference frame, we didn't call it like that, but a system of bodies that can be used as a reference when you formulate the laws of mechanics. And what Huygens did do very cleverly is an operational construction of such a system of bodies. He says, he calls it inter se quiescentes corpora. Those are old manuscripts, never published in Huygens' lifetime, and published only in the early 20th century. So it cannot influence any of the later writers on the stories. You will see that many other people, several people came back to the same idea. But it's in those manuscripts by Huygens, very penetrating manuscripts. And so what are these, well, if you know them, with bodies that are at rest mutual to each other, resting with respect to each other. So what Huygens says that we know empirically that it is possible to pick a system of bodies that are subjected to completely free bodies, not subject to any force, and in such a manner that their mutual distances are constant forever. And then this is, and any such system of body I can take as a, I can define as a reference frame in which the laws of mechanics are valid. It's a construction of this frame, if you wish. And immediately, of course, he shows you that you can pick, in fact, there are necessarily an infinity of such frames, and they are all moving uniformly with respect to each other, and linearly with respect to each other. So you have this idea of operationally constructed class of reference frames that are all strictly equivalent for Huygens. There is no absolute space at all. For Leibniz, well, very famously, Leibniz concept of space is purely rational. It's a defined space as the order of coexistence of objects, if you wish. But Leibniz, it has, late in the century, there is a discussion between Leibniz and Huygens, because Leibniz is fairly ambiguous because he has a problem with, on the one hand, he's completely agrees with Huygens that motion is always motion of something with respect to some other things, okay. But on the other hand, he has the concept of a living force, and a living force is something very important in Leibniz's metaphysics and metaphysics. But for living force to be defined, it can be defined only with a specific space, reference frames, if you wish, because evidently the living force will not be the same in another moving space. And so he has trouble, and in fact there is no really, Leibniz never solved it to best knowledge, never gave any plausible solution. You can see he's clearly embarrassed in the correspondence with Huygens. Okay, but now let's move to Euler. Euler certainly was perhaps with D'Alembert or a few other French and Swiss people also one of the most important people developed in Newton, generalizing Newton mechanics in the 18th century. And so of course it's very important to look at how Euler discusses these topics, and he has a more philosophical, this is very rare, an Euler article for 1748, in which he defends absolute Newton's absolute space. He really defends this concept of Newton against what he calls a metaphysical point of view. He doesn't name Leibniz, but obviously it's Leibniz because he also speaks of the order of coexistence, etc. So, okay, he doesn't want to, for obvious reasons, he doesn't want to name Leibniz. But then he tells you that space necessarily is necessary as a physical entity, it's as physical reality, because we need to explain inertial behavior. You need to justify inertial behavior, and so Newton was right to introduce this concept of absolute space, saying, well, there is one possible alternative. You could conceive that the cause of inertial behavior is a celestial body very far from us. And, but he tells you, well, this is too implausible. How could the stars affect the behavior, the inertial behavior? It is responsible for the inertial behavior of bodies that are our scale, near us, for bodies near us. So it doesn't seem a possible option. So to him, absolute space is a necessity. And then comes Kant, who wavered several times in his analysis of space, but the most mature conception is in 1786 that he has in the context of Newtonian mechanics. Is in the Metaphysische Anfangsgründe, dann hat Wissenschaften. And here, clearly for Kant, again, there is no absolute motion, just like for Huygens and all the other ones. But there is true rotation in a mechanical sense, because by mechanical experiments, like Newton's famous bucket, you can actually prove you have a true rotation. So it's a little subtle, but I don't want to enter all the complexities of Kant's discussion, but I give you only the result. So all inertial systems for him, that's important, just like Huygens, are strictly equivalent. There is no absolute space in the sense of Newton. He does use the phrase absolute space, but it's completely different. Absolute space for Newton is a structure, it's a generic form that is applied to all possible reference spaces. Okay, it's a Euclidean structure, basically. That's what he means by that. There is sometimes some confusion in literature because, but there is an absolute space for, yeah, okay, but it's not Newton's absolute space. Let's move to the 19th century. In the 19th century, there were many, both in British and German context, but there were quite a few criticisms of the foundations of mechanics, often for pedagogical purpose. People knew when you teach, you want really to be clear about the foundations. And so you have first James Thomson, the engineer, and he's the person who coined the expression reference frame. That comes from him. That everyone using them, you have explicitly reference frames. And just like for Huygens, or a little like Huygens, not just like, they are constructed operationally. So it has a class of inertial frames that are, he's an engineer, so it's a little funny, but in fact he constructs his class by having some kind of kinematic devices that link the reference frames to each other so that they can move only uniformly with respect to each other. So this is a bit tricky, but it works. And it's a complicated way to do what Huygens had achieved, which much simpler. Then you take Ernst Mach. So, you all know that for Mach there is only a relative motion too. And in fact, in the end, Ernst Mach does exactly what Euler had judged an implausible option, that he sketches a theory of mechanics in which inertia is determined by distant bodies, celestial bodies, inertial behavior. And lastly, perhaps most interestingly, you have Heinrich Schreins, who his treatise on mechanics, Foundation of Mechanics, was published the same year as Mach's Mechanik. And I think it's just from the power of the critical insights contained in this book is absolutely remarkable. It has never been translated in English to the best of my knowledge, and it's little known, but it's a remarkable piece of depth of analysis of the foundation of mechanics, I think. And so what you have, the Huygens notion of constructible or operationally constructible reference frames that serve as inertial frames is replaced here with a notion, which is a little more realistic, if you wish, of a testable preferred class of reference system. You can concretely build a reference system, and then you can experiment in this frame to test whether or not it's inertial. You will perform experiments again like Newton's bucket or variants of that, in order to know if you are in a referential system of that, and then you select this class, and then you can show very easily that you have the usual property of this class, that any member of this class is obtained by uniform rectilinear translation from another member of the class. And so you have this inertial class of system. And what is most interesting is that there is a deep analogy that Heinrich Schreins make between this class of inertial system and the class of Cartesian possible coordinates for points in a Euclidean space. Okay, in space. This is just the same thing. Just as in Euclidean space, you can look at the same points, which is intrinsically defined as a point of your Euclidean space. You can describe it with different system of Cartesian axes and a different system of coordinates. Say, well, you can do the same event, to use an anachronistic term. You can describe it in different reference systems. This is just like different coordinates in space. And so he has this idea of, in fact, an intrinsic object which is behind the set of the class of equivalence of inertial system. So this is very nearly, in fact, how we conceive nowadays the the structure of Galilean space-time. Okay. And again, there is no absolute space, of course. Okay, now I think I'm ready to conclude. Well, both in the history of the relativity principle, but also I think in his present conceptions of it, I think one can clearly distinguish three components of this principle. First, it is an empirical law that can be empirically verified, and this aspect was recognized already by Galileo, as we saw. These empirical aspects and repeated by many other people, and also anticipated actually by others. But anyway, then you have the constructive principle, which I think was really pioneered by Huygens and revived in the 19th century in this French tradition with Laplace and this French tradition of textbooks of mechanics and the baccalaureate, etc. Well, you use the principle as a constructive tool, construct the theory of mechanics. And then you have an epistemological aspect, which is introduced by Huygens and reactivated by Kant and then by Einstein for the 19th century, that tells you, look, if you, in fact, to put it in modern terms, the principle of relativity is a principle of symmetry. And now in your theory, in the kind of representations of theoretical representations that you have for mechanics, there shouldn't be any asymmetry that is incompatible with this phenomenological symmetry expressed in the relativity principle. This is one version of Occam's razors, if you wish. And this aspect, of the epistemological aspect, is clearly introduced by Huygens in his philosophical manuscripts. And again, well, I just already told it, but it also occurs in Kant and Einstein. And now, once you are equipped with this distinction to these three components, you can see that what does Poincaré do in the late 19th century? Well, it extends the empirical component of the principle because he considers that the principle of relativity applies not only to mechanical phenomena but also to electromagnetic phenomena, and in the end even also to gravitational phenomena. So he has, and also develops very forcefully the constructive aspect of the principle. He's going to use it as a constructive tool, also as a gauge to refute or to certain theoretical proposals, and that if they don't match the principle, forget it. So it's really a constructive principle. And now look at Einstein. Well, what happens with Einstein is that you have the three aspects. You have empirical aspect, you have a constructive aspect, obviously, and you also have, unlike Poincaré, you have the epistemological aspect. Whereas Poincaré is perfectly willing to maintain the ether in his relativity theory, Einstein doesn't want an ether, or at least he doesn't need it, and because the ether is kind of becomes parasitic because it introduces this kind of unwanted asymmetry that is incompatible with the symmetry expressed in the relativity principle. And this is why Einstein doesn't need the ether in the end. And then, of course, after what I told you, you can see that there is a rather strong similarity here between the ether, the concept of ether, and the concept of absolute space, because in the end, Einstein rejects the ether for a reason very similar to this epistemological aspect of the relativity principle. Is used in both cases. One case to reject absolute space for the history of mechanics, and then in the case of relativity theory, to reject the ether, So Is this a coincidence? Of course not. It's not a coincidence because I showed you that Einstein was aware of this debate on the foundation of mechanics. That's what I didn't tell you, but I'm pretty sure that you all know already that Einstein read Mach, and especially the mechanic. And then in Mach's mechanics, you have a discussion of the foundation of mechanics, including all the proposals that were made, which is, for instance, Heinrich Heinz, of course, whom you know well, was his colleague in that is discussed in the appendices of Boltzmann mechanics. And so all this, the criticism of absolute space, and how you, for what reason you should get rid of it, and how you could get rid of it in the context of mechanics, all of this Einstein was perfectly aware. So there is really a natural path from this rejection of absolute space to the so I think in the end, that Einstein was not lying at this London conference when he said that this is a line that goes back to many centuries. Thank you for your attention.
Let's take a 5 minutes break. Oh, and also, I attended a conference Wednesday in Liège, and there was a nice rule. So if you raise your hand, it's for a new question, but if you raise your digit, it's for a follow-up.
The Oxford.
Maybe we should try this.
What is it for questions?
Questions, follow-up.
I think it's an Oxford.
It's possible. Okay.
Yeah, so first of all, thank you very much for this very interesting talk. My question was mostly actually a curiosity, because I've seen that normally when one talks about the origin of inertia as due to very far objects, very far stars, normally thinks about the Mach hypothesis. So here you presented the fact that Euler, if I'm not wrong, was strongly against this idea, and so he was basically referring to the Newton's bucket thought experiment, right?
Or any similar. Well, no, just any kind of inertial behavior. In fact, that you know that you need some explanation of inertial behavior.
Yeah.
And so for Newton, for Euler, just like for Newton, it must be absolute space. He cannot imagine anything. And of course, from our point of view, we can have a structure which is defined by this classical by this class of inertial frames, and define the structure of space-time. But this is a very abstract way of doing things, which is not conceivable for Newton and Euler. And so for them, the only things they can see is that there is an absolute space.
No,
with all the problems that it can create, but they rather have the absolute space than nothing.
Yeah, exactly. But I was trying to figure out where this idea that inertia could be due to a very far object originally came from.
Well, I'm not aware of anyone suggesting it before. I think actually maybe Newton himself actually followed it. I think I know exactly what's the question.
That was my hypothesis, but I'm not sure about that.
Yeah, I think there is in manuscripts of Newton discussion, but again very dismissive, immediately dismissive. Euler may not have been the only one, but that's the only one I can instantly remember for sure. But, but I wouldn't venture to say that no one.
No, but that's already a good indication. And the second point is, what was Kant's take on this idea when he talks about the truth of rotation that you mentioned in that slide?
Again, it is indeed Newton's buckets, or two balls connected by spring, or whatever. You can variety of that. But the fact is that for Newton, it has correspond to his table of categories. But there are 4 stages in his mechanics, but in this philosophy of nature, and they defended in the metaphysics is that there is what he calls the phoronomy, which is roughly kinematics. Then you have the dynamics that deals with forces, and then you have a mechanical stage. So as a kinematical stage, the motion is purely relative, like for anyone else. I mean, anyone else since Huygens and Leibniz, etc. And that at the mechanical stage, you have the concept of true motion that can be the truth can be demonstrated by experiment, and it doesn't conflict with the complete relativity you have in the canonical context, because this belongs to different categories. So there is a whole philosophical background behind that. I know for you it may be strange to have nowadays to have this it sounds a pretty weird distinction between having a true distinctions between true motion and real and absolute motion. The difference between true and absolute, it seems pretty weird. But for him, the motion, like you do the Newton-Buckets experiment, you still need to specify a reference frame, and in that case, it would be the reference frame of the fixed stars, for instance. And so it's always, when you describe these experiments, you will do it always by the motion defined in the kinematical sense. And but then you find that the experiments show that there can be an effect of observable effect of motion, which you call true in the mechanical sense. But it's a rather subtle, difficult distinction, and it's not entirely foolproof, because I think the problem in the metaphysician field is that Newton pretends not to have separated quite well the real of the four categories of understanding, and in fact, if you look carefully, he doesn't, because already in the kinematics he uses some things that belong to the schematic, and then in later sections he uses notions that appear in the earlier ones. So there is constantly things traversing the borders between the categories, and unconsciously, I think he's not quite aware of that. And so the whole strategy of the metaphysician is, in my view at least, I think Michael Friedman used to have a much more positive view, but me, I'm much more critical of it personally. And I think superficially it looks like a beautifully well-organized system. It fits quite well the table of categories. If you believe in it, of course, you have to first believe in the table of categories. But if you look more carefully at the implementation, there's many questions you can raise.
Okay, thank you very much.
Yes, thank you very much for the talk. I have a question about this Strein's conception. Strein's, yes. I didn't understand why you call this epistemological tradition. Maybe I just didn't get what was his idea, because I understood that he has developed a set of different tests of how we can select reference systems, and then made analogy to transformation of coordinates. But why is it epistemological sort of strand of?
I use this qualification not only for him, but for anyone who basically rejects the absolute space, arguing that he's one of the people, but he's not the first.
Yes.
Huygens rejects absolute space precisely because he doesn't have any, it doesn't have any operational significance, and it doesn't, it suggests that phenomena should be different in spaces moving with respect to the absolute space, which they are not. So it's all of it. This is what I called you. Of course, with that for Einstein, this is one of his explicit major motivations, and actually the article of 19 of Einstein. Just with that, this whole idea of the asymmetry in the description of electromagnetic induction, which is the beginning of the article of 1905, is just the expression of this epistemological razor of Occam that Einstein is going to use to construct his theory.
Okay, well, merci beaucoup. I have many questions because, as you know, I worked in those issues quite a bit when I was a graduate student and a postdoc. But I have a first remark of terminology, because you used the term constructive, and that means, according to you, that you have a principle that could serve as a premise to deduce and to prove a theorem.
Yeah.
Whereas, as you know, Einstein distinguishes between constructive theories and principal theories.
Right.
And the principle, so Einstein uses the principle.
Yeah, I should have used the word construct.
A principle of relativity to, like in thermodynamics, to deduce some laws. And he constructs that with the kinetic theory, in which you have a bottom-up approach, which you try to construct a mechanism for which you can, on which you can underpin the phenomena. That's a side remark. The second thing is about the.
May I answer this one?
Oh, sure.
When you are right, my terminology in this respect was not very felicitous, and I should rather have said an organizing principle, for instance, because indeed otherwise you have a conflict between this terminology of Einstein, which is not Poincaré's, because Poincaré actually didn't use the expression constructive principle, although what he has in mind in his opposition to the physique des principes is the physique des forces centrales, the Laplace physics, which is a kind of constructive physics in the sense of Einstein. So the distinction is actually quite similar in Poincaré and in Einstein. And but indeed, when I use this expression construction, it's certainly not a construction bottom up, but up to bottom. It's a reverse way. And so this construction is ambiguous, and you're right. It's not a felicitous terminology. I apologize for it.
Okay. I know you said at one point that there is some similarity between Galileo's ship and the Einstein's equivalence principle.
No, not a Galileo's ship. Between what Bélanger calls the principle of relativity, or what I call accelerative relativity, which is a theorem for Newton, and there is actually I'm not the first one to have remarked that, but this corollary of Newton has some similarity with the equivalence principle, but it's not restricted relativity, and it's not a Galileo bot. Galileo bot is limited to uniform motion, so it's really restricted relativity.
Yes, but okay.
Yeah.
Then, okay, so let's look at the principle of relative velocities. Then, from what I understood, because I didn't know about this principle of relative
accelerative relativity.
Yeah. Because then, as far as I understood, is that when you are in a system, then you can accelerate some bodies, and then of course you will want to be able to detect that this whole system is accelerated or in uniform motion. Okay, so the relative velocities are going to be the same, and the parallel with the Galileo's ship is this: if you are inside the ship, which is in rectilinear motion, of course, then if you push something inside, by doing this, you are not going to be able to detect whether the ship is in motion or at rest.
Mm-hmm. Okay,
that I think it's to be the. That's why how I understand the principle of relative accelerations. Is that what? Sorry about the terminology because I don't master the terminology. Whereas in the Einstein equivalence principle, is that in a particular case, it's in a uniform gravitational field, then you cannot distinguish between if you are inside a cabin, you cannot distinguish between decide whether you are in free fall in a uniform homogeneous gravitational field, which doesn't exist in nature, but that's and an acceleration, I mean an external acceleration which is pushing or pulling the cabin. So the difference between the equivalence principle and the principle of relative accelerations is that the acceleration takes place inside the cabin by someone who's accelerating the bodies, whereas in the case of the equivalence principle, it's the whole thing that is accelerated or...
Not really. It's still the whole. In both cases, it's a system that is immersed in a gravitational field for Newton and for Einstein. But it's just the emphasis is different. For what Einstein tells you is that if if you are like on Earth here, like in this room, we have approximately a uniform gravitational field, okay? But you could mimic this. You could have by simply having suppress the Earth below you, so no attraction of the Earth, no gravitation. But you can get exactly the same. You can have artificial gravitational, like you have in a celestial vessel that is accelerated. You can recreate artificially the gravitation. So the idea is that you can simulate gravitation by accelerating your reference frame, or laboratory, if you wish. Okay, you can. That's Einstein's idea.
In a special case.
So formally, it's actually. If you restrict yourself to mechanical phenomenon, the justification is exactly the same for this. This is just a way of phrasing this, the same principle as the ones that you find in Newton or the theorem that you find in corollary of Newton. It's just that the emphasis, this emphasis of Einstein is he wants to be, because that's important heuristically for him, he wants to be able to mimic relativity by by acceleration of the reference frame. That's what he wants, actually. That's what he will use heuristically. That in order to, for instance, to investigate the effect of gravtation on light, he will say, well, this is the same effect as the effect of looking at light propagation in an accelerated frame. That's how he will derive the deviation of the gravitational deviation of light. And of course, we have nothing similar in Newton. Because here Newton is just thinking in terms of, he has only mechanical phenomena and gravitational forces, he has nothing else in the game. And so, the only thing that Newtons care about is that he doesn't want to simulate a gravitational field. On the contrary, he wants to eliminate it. That's exactly the opposite endeavor, is that he wants to tell you, okay, you can reason on Jupiter and his satellite as if there were no gravitational field, you see? So the intention is different. The mathematics behind is the same. It's all, the fact is that if you have, you write the laws of motion for a system of particles, it will be F equal ma, for everybody, and so forth. But in those relations, if you add the same constants to every A in those F-Gal-Ma relations, you change nothing about the relative motion, right? And so that's all what Newton is telling you.
No, but I was not. I expressed myself. I agree with what you said, but I was referring. I didn't phrase my remark carefully enough. I was referring to Bélanger and Viol principle. Yeah. So what I understood is that you have a system of particles which are moving, and then you give accelerations, parallel accelerations to those particles, and then you don't change the relative.
Yeah, you give a common acceleration to each body. To the other accelerations that would be impressed by the internal forces. Okay. You add a common acceleration, implicitly of a gravitational origin, and then nothing is changed for the relative motion.
Okay. And then
although something is changed for the absolute motion, of course something is changed because you have added gravitation, but so it's a relative motion.
Yes, and then the parallel with the equivalence principle is that if that's a uniform homogeneous gravitational field is giving to each particle, photon inside the cavity the same acceleration.
Exactly.
All right.
Yeah, that's all right. It's really it's a different modality, even though it's formally the same thing, but the modality application and the heuristic use of it is very different.
Yeah, it's a heuristic
you can,
because...
And from the philosophical point of view, you can certainly not say it's the same thing.
Yes, okay. Then, I don't know if there are other questions, because of the ones you monopolize the...
En ligne, il n'y a pas de questions.
No, nothing online, so go ahead.
So then, as you know, for the principle of relativity to be valid for both electromagnetism and mechanics, there is the possibility to take the invariance group, mathematical group, to take the invariance group of Galileo, the invariance group of mechanics, instead of the invariance group of electromagnetism. And this was attempted by Hertz.
Yes, yes, yes.
Hertz proposed, why, of course, at the end of the day.
But the thing is that you can do that probably.
Einstein won, but at the beginning, since if you want a principle of relativity which would be valid for both electromagnetism and mechanics, why don't you take the Lorentz group of invariance? A priori, that would be an equivalent option. But why did Einstein, and at that time, what was the reason he chose, he made the choice to take the Lorentz group, the invariance group, by the principle of the invariance of the velocity of light, which is,
Well, a bit,
I don't know, it's a question. It's a historical question.
It is, because you don't have the theorem in your reference frame, and then it becomes natural to define time and synchronization through by optical means, and doing and taking the velocity of light as constants, which is the same in any for any reference frame, in any initial frame. So that's the whole idea. And instead, for Poincaré, there is still a privileged ether frame that gives you a privileged concept of time, and the times it is synchronized and defined by synchronization protocol in the ether frame is regarded as a true time for Poincaré, and the other ones, no. You have a symmetry of your basic equations and of the and of the observable phenomena corresponding, which is expressed by the Lorentz group. But Poincaré, even though he's a mathematician, doesn't want to define the space-time structure with the attached group. He's not following his own Erlangen program type of methodology that he has in mathematics, where you define a space-time structure through the attached group. And he doesn't want, and he knows he can do that, but he doesn't want to do that for psychological and pedagogical reasons. He bets that physicists would never accept to take such a step. They would always. So he was trying to adapt itself to the common people. He could think like Einstein, I think, but he didn't think it was reasonable.
But I was referring to Hertz.
Compared to Hertz, well, Hertz is a problem that it's really a different kind of theories. Is that just as in Maxwell's, when Maxwell deals with electrodynamics, really for Hertz, the ether, well, is very physical thing, because not only it serves as a reference frame, but it moves, and the ether has a velocity. Every part of the ether has different velocity in an ether theory. So of course, it becomes very natural in this context to consider the body. When you apply the relativity principle, you should consider the ether as a body in par with other material bodies, because just as other material bodies, the ether, every point of the ether has this specific. It's a deformable medium that has every point of it has a specific velocity, and so in that case. Sure, you can still have a relativity principle, but the relativity principle applied to a mechanical system that includes the ether as one of the mechanical bodies. And then if you do this way, yes, the Galilean group, as you say, works perfectly well. But this approach becomes very artificial in the context of Lorentz theory, where you have a Lorentz-Fresnel theory, where you have a purely stationary ether, where the ether is really a ghost of the ether. The only purpose is to serve a privileged reference frame. It doesn't have any dynamical properties. It can't work yes, it carries energies, therefore that's a dynamical property, but it cannot move. I mean, it doesn't have it doesn't, the ether is completely rigid and is therefore forever. And so in that case, and knowing that, moreover, any experimental attempts to observe effects of motion with respect, global motion with respect to the ether, to astronomical observations, can give you a zero result, including Michelson-Morley and whatever you want before that first order, since Fresnel, and so. So you have an incentive really to do like Poincaré said, well, okay, look, but we have to stop expecting effect of motion with respect to the ether, and instead we should rather be critical about the physical reality of the ether, some kind of physical substratum, and that we should, in fact, in his earliest writing on this issue, Poincaré said, et notre éther, est-ce qu'un jour nous ne l'abandonnerons pas? He didn't himself give it up, but he was perfectly aware of the fact that it was an entity that had certainly didn't have the same reason of being as other physical entities from his own point of view.
Okay. According to Hertz, there was no, as far as I know, a privileged reference system.
No, there is none, because there is no ether frame for ether.
Yeah.
There cannot be an ether frame because the ether moves itself and it's not deformed.
Yes, but according to Hertz, according to him, what was the main reason to prefer to prefer mechanics over electromagnetism? Is this because it's a habit or common sense, or
no?
Was there deep physical reason why he wanted to privilege mechanics over
it's simply that if you look at it from a Maxwellian point of view, where the electromagnetic field, the electric and magnetic field are regarded as properties, in fact, even mechanical properties of the ether, of a mechanical medium. Then when you have, it's very natural when you have electrodynamics of moving bodies to suppose that the medium follows the ether, it follows the bodies, the motion. You have a kind of combined medium of ether matter that have only a single velocity, and that's the very simplest option that you have, in this theoretical framework. And that's exactly what Maxwell did himself to derive some results of the electrodynamics of moving bodies. And so that when to obtain the induction phenomena, for instance, electromagnetic induction phenomena, Maxwell used this approach of the co-moving ether, which is generalized by Hertz's theory. Is just a generalization of this idea of Maxwell.
Okay.
And it's done systematically in a symmetric way with respect to the electric and magnetic fields. And so, in this whole mechanical ether-based approach, really the simplest idea you can have of the interplay between ether and matter is just that the ether was following the motion of matter. Because it was not obvious to be able to imagine how matter could travel through the ether without, like Lorentz did. So this becomes possible in an atomistic conception like Lorentz, where while you have matter is made of tiny particles that can likely move through the ether without disturbing it, and that ether remains at rest, even though there are things moving through it. But if you have a continuous approach like Maxwell did, of electrodynamics, where bodies, electrified bodies, etc., they are macroscopic bodies, they are complex bodies. It's not natural to suppose that these things move through the ether like that without disturbing the ether at all. You see, and so if you look at the heuristic behind Maxwell, which is in part transferred to Hertz, it is natural to reason in this terms, and it was rather revolutionary to do what Lorentz did, and he did, as a first step to relativity theory. Lorentz Lorentz's achievement is, as Einstein himself recognized, of course, is extremely important because there is a huge conceptual gap between Maxwell's original theory and Lorentz's theory, which is forgotten today. Physicists believe that Lorentz and Maxwell is just sort of, he just added the Lorentz force or whatever. No. This is a very deep conceptual change between Maxwell and Lorentz. And that explains why, indeed, the natural group of transformations, to put it in modern terms, is a Galilean group in Hertz's theory, and in Lorentz's theory, it becomes the Lorentz group. Because of that.
Okay, thank you.
Marco?
Thank you so much for the talk. Concerning the last slides, the conclusion, the principle of
Sorry.
Okay, the modern principle of relativity, the three components. This is really a curiosity I with native concerning this. The empirical part, commonly recognized since Galileo, okay, but so general question. Empirical is kind of implies some ontological commitment. It seems to me that from a very outside point of view, that if you rework some empirical finding of the past, maybe the ontological idea, of course, is different, but what do you think about these two dimensions? Is the same? How do you work together in that part? If it's relevant, I don't know.
I think, well, of course, this word empirical is like an umbrella word, it's not very precise. And of course, when you state a law of relativity, like any law of physics, there is some induction behind it. That you made some observations, or actually you didn't make them, or made some of it. Of course, Galileo can be sure he had trouble on the boat. He was working for the Venice Arsenal, etc. He knew when he didn't fly like we do nowadays. Yes, sure, you can see that there is some truth to this relativity. But then, of course, to accept that it's general truth is an inductive step, and then you may interpret this as injecting some ontology into it. I don't know, but there is a jump. But I really didn't discuss this point because it depends for any kind of physical law, so that's not specific to the case of relativity, and it's more or less. It's pretty well emphasized by Laplace, actually. If you look like, he discusses, very specific experiments you can do, or some have been done actually on Earth. It cannot be a very, very accurate thing because Earth rotates. It's not an inertial system. But he worked Laplace in the approximation of where you can neglect the rotation of the Earth. And in this approximation, we have experiments to tell you that really, this relativity is something that is something you really have tested experimentally pretty well. But again, you test it in a few cases, and then you need an big induction in order to assert it's true generally. Right?
Yes, if I add something. I think that you mentioned the mast experiments you have approved. You have a mast,
right,
and then you drop a stone from the top of the mast, and then according to Galileo, but he didn't make the experiment himself. The stone must fall at the bottom of the mast, just at the place where the mast is put in the boat. But in fact, Galileo himself realized that it is not true, because if you take a very long mast, you will have
the eastern deviation.
You have a bigger circle
because of the rotation.
So you have here the Earth. words. So the tangential velocity of the stone, all things being equal, is bigger. So the stone before before
it's absolutely
he
true.
was aware of that.
For Galileo himself, it is an approximation because he's aware that the rotation of the Earth it brings in a correction which we call now la déviation vers l'est in French. And, so that's what you have, but the case of Galileo is complex because sometimes he's careless and he reasons in terms of rectilinear inertia. Where he knows, well, from his point of view, inertia is sometimes circular, sometimes not. So it depends which sections of the writings you take. So Galileo is never rigorous. He's ingenious certainly, but not rigorous, never. But still, the basic idea is there. It's powerful, convincing, etc., etc. But it's actually amazing that he's aware and he derives actually the correct deviation, as you say, for the correct correction for the mass problem. The whole history of the mass problem is very funny because before Galileo, many people claim to have performed the experiments and with different results. Some of them probably had the foot was confirmed to Aristotle's views. So you see, forget about easy induction in this matter. Right?
Yeah, I had a question on this move from a statement that is an empirical law, and it's moved to the constructive or organizing status.
Yeah.
You said that Huygens and maybe Euler did this move.
Yes.
So it's a change of status. It's the same statement changes its status.
Yeah, it's
the
statements.
I was wondering whether it also
the same property.
For at least some of those guys, if it also changed its meaning, because when it was considered an empirical law, it stated a fact.
Yeah.
But when it's elevated to the rank of a principle, does it state something else than a fact, maybe an objectivity requirement or some a priori truth? Or
Where you go really beyond a mere induction, where there is a stage of induction already that takes you to the empirical law, and then just as Poincaré says, at some point you use this expression, élever la loi, en principe, you elevate the law to a principle. That means that, at least psychologically, at least, you cease to be to question it, and you say, well, I forget about the potentiality of future experimental refutation of this law or limitation of this law, and I will decide in the future that this is absolutely true, and that can use it as a point of departure. But nothing is strictly rigid for Poincaré. It also tells you what, well, any principle, maybe someday after all we will have to give it up. And there is this famous essays on la crise des principes, de Poincaré at around 1900, where precisely he was quite bothered because it seems to him that every major principle seems to be in danger at this stage of history. And so it's more like a change of attitude. He didn't certainly phrase it in metaphysical terms, and that was not Poincaré's way of speaking, but the function and the authority of the principle that it has in your mind has changed.
But for more Kantian oriented mind?
Well, Poincaré was some sort of neo-Kantian anyway, but the fact is that for Poincaré, the main the essence of Poincaré's synthetic a priori is really the group structure, and this is the fact that in order, the phenomenon, if you want to be able to have a precise mathematical theory of the world, there must be some sort of basic homogeneity that tells you that, for instance, that there is a similarity between phenomena happening in infinitesimal domains or neighboring consecutive infinitesimal domain, and that's this is a group structure that is attached with this basic reproducibility of phenomena from one element to another. This allows the application of calculus to physics, and so group theory is very important because our ability to understand the world, at least in the mathematical physical manner, is due to this kind of homogeneity of the world, which is captured by group theory, by the structure of Lie group for Poincaré. So this is very important, and of course his way of seeing principle of symmetry, like principle of Poincaré, is so essential. Indeed, is because they are attached to a group structure. So his mathematical thinking and his general thinking about the possibility of mathematical nature are all correlated. So it's an interesting question.
Yeah, it's more of a sort of side question. It's about this change in the formulation of the Newton's law, which was, when did it happen that everyone accepted the proportionalist reading rather than?
You see, first, I think it's a Swiss Newtonians, and in the early 18th century, and also even before them, François Varignon, less known figure, a French geometer, I would say, in those years, geometre, and who formulated Newton's law using the concept of acceleration and using Leibnizian calculus, actually. So, of course, Newton had his own calculus. He had those dot derivatives of acceleration. But as a matter of fact, he's still in the Principia. When Newton wants to derive important laws, for instance, Kepler motion, he does it. This famous fan figure. He does it by a succession of impulses, and you have a very simple geometrical reasoning there. You don't need to know any infinitesimal calculus, and you get the right result, right? And so Newton fought in this term, and it remained popular. I think because of the authority of Newton and the Principia, people were still learning mechanics from the Principia. I think at least till the late 18th century, and so this remained. But it's true that people like Euler or like Varignon, the Bernoullis, etc. They all knew how to formulate the law directly as so I would say it will be very hard to give you a precise date, because I think it's just a gradual process, and different people use different ways. But you can say that it's interesting to see that Laplace still favors the discrete conception, and maybe because it serves its purpose of a simple derivation, actually, of the second law from the relativity principle. Because it's only in this conception of the law that you can use restrictive relativity to derive Newton's second law. Otherwise, it's not enough. It's easy to see that you need something else. So something, because you could, for instance, add a third derivative or any kind of higher order derivative, it's still compatible with the relativity, restrictive relativity, right? Any higher order derivatives added to the equation of motion wouldn't change anything. So if you want to, it's only the discrete conception that works.
I have maybe a last question, but it's a big one, but I hesitate to ask it because I wonder if it's just me who does not understand something. I've always been confused between two different, at least what occurs to me as different senses of relativity. On the one hand, you have dynamic or Galilean relativity, which means that the laws of physics or the laws of motion are independent of the state of motion of the system to which they apply, or
The reference system.
the reference system, right? But you also have this quite different idea that motion is only relatively described, never absolutely described,
Yeah.
because motion can only be reported relative to another
Right.
viewpoint attached to another body.
Right. And that's
So
two different
that's
things.
two different ideas, and
Yeah, that's what bothered Poincaré actually. You just formulated it just like a Poincaré does
Okay.
when he discusses this topic. He shared his talks on mechanics, and what Poincaré tells you is that from a logical point of view, of course Leibniz is right, and that motion is always motion over something with respect to some other things. It doesn't make any sense to speak of motion in a vacuum. So in this token, we should expect any reference frame to be equal to another one, and then. But when you do experimental mechanics, we see this bizarrely this is not true, and Poincaré regards this as a major puzzle, unsolved puzzle. Is that in fact we don't have any conceivable concept of space that enables you to do such sort of selection. If you believe in the Leibnizian point of view on motion or being purely relative, you couldn't have the relativity principle in the sense of restricted relativity. It should be general relativity, not restricted. And so it really, but what is behind there is that, and which will be reinforced by general relativity later, is that space, and then later, well, actually it's already space-time in the Galilean case, but there's different space-time for general relativity and for Galilean relativity, is that it's a physical entity. And contrary to what Marx thought, like this is an anti-Marx aspect of Einstein's relativity, is that the space-time manifold, it's a physical object. It's not just an abstract reference. It has its own dynamics, and it's coupled to the dynamics of Marx. And of course, it becomes much clearer in general relativity precisely because of the coupling between the space-time manifold, wherever it's completely decoupled in the Galilean framework. But even though it's decoupled, it's still true, and this is what was right about Newton's intuition of absolute space, that you need a concept of space, but Newton should have said of space-time, that enables you to account for inertial behavior. So inertial behavior is only conceivable unless you adopt, again, Marx's rather extraordinary viewpoint, but it's only conceivable if space-time is a physical entity that has causal powers.
I agree with that. Yeah. That's the way to solve this aporia. There is a space-time with a structure, the metrical structure and the fine structure, curvature, and that exists in some sense.
The only thing is, of course, Newton in his time could conceive a space-time structure which would be such an abstract thing. It could be defined only like a classic reference frame, like a class. It's what Huygens has. That's what's so amazing in Huygens, is that he's close to the truth in a way. Huygens, the way he presents mechanics, he gets right at the essential structures in his philosophical reflections already. And you see more striking even in the case of Heinz, and that's why I want to resurrect Heinz, but it's worth reading in a way his book for many other reasons. It's really excellent. Of course, Marx is also excellent, no doubt, but it's very provocative and deep thinking, but in both cases.
Thank you again.